Okay, now you can go. Thanks.
Okay, thank you. Good morning to everyone. It's a pleasure to me to present Professor Shanzhong from the Department of Mathematics of the Capital Normal University. And the title of the presentation is Monodromy of Complexified Planar Kepler Problem. It's a joint work with Peng Gu. And you can start, Professor Shanzhong. It's a pleasure to us listening your talk. Thanks. Guys, take off the camera and the microphone, please.
Okay, I will start. So this is the outline of my talk. At the beginning, I will give a very brief introduction of the planar Kepler problem to fix the notation. I think everybody is very familiar with this part, so I will be very quick. Then I will go to the reason why I'm considering complexification with the Kepler problem. Then I will show you my really concern about this problem. As last, I want to share with you some problems that I cannot solve. So let me start from the planar Kepler problem. So as we know, this is the phase space of the planar Kepler problem with the canonical symplectic form. This is the Hamiltonian of the Kepler problem. Note here that here to make this Hamiltonian function well defined, we need to remove the origin of the configuration space. Later on, when we complexify the problem, we need to also complexify the Hamiltonian function. So we need to make this part meaningful. So this because when we switch these two variables to be complex, here will be multi-valued. We need to fix this problem. This is one of the main stackle. So also it's well known that this planar Kepler problem is a Hamiltonian system. We know that for this problem we have two first integrals. One is the total energy, that is the Hamiltonian. The other one is the angular momentum due to the rotation symmetry of the problem. They are quite well known. Also, we know that with these two first integrals, this planar Kepler problem is completely integrable. So for me, what's the meaning of complexification? So it's quite usual in the literature. We combine these two real variables to a complex variable. That it's a very nice idea to use a complex variable to study especially planar n-body problems. For example, when people like Cauchy study the Kepler equation, they use ideas from complex analysis. So this is the relation between the true anomaly and the eccentric anomaly. This is used to solve this Kepler equation. Here for us, when we try to complexify the mechanical problem, we replace each real variable by a complex variable. So instead of the configuration space real R2, we consider the C2 as our configuration space. One of the motivations is from the recent activities in quantum field theory. So people like this, they consider the kind of way to treat path integrals in quantum field theory. They claim that they need the complexification of this path integral for some physical reasons. In fact, this idea can be traced back to the work by Ballin and Bloch, two French mathematical physicists. In fact, they already have this kind of idea to complexify the path integral. But I would say that at that time, for them, this kind of complexification is a kind of techniques. But for these people, they really need the complexification. More precisely, in physics, especially in quantum field theory or quantum mechanics, people are interested in this kind of integral. Of course, this is an infinite dimensional integral. It's called Feynman path integral. Both the complexification of the action, this is the action part. This is the method. Of course, mathematically, this method is not well defined. Physically, the people argue that they need the complexification, not only the action, but also the method. So at the semi-classical level, this means that you consider the critical points of the action. Then you do the asymptotic expansion around the critical point of this action. This is called the stationary phase principle. This can give you the sum of the quantum effect. If you study the classical story for this, so you need to consider the Euler-Lagrange equation of the complexified action. So this gives you the holomorphic Newton equation. This is right in this way. So here, this z is the belong to the configuration space. V is a holomorphic function of z. This is the potential. Here, T is still real. So people from a quantum field theory argue that they need the complexified solutions, including multi-valued ones and singular ones, to get some exact result about the partition function. So this is one of the motivations. In fact, when I searched in the literature about the works on the holomorphic Newton equation, in fact, I could not find many. I only know that some works by Bender and his collaborators, their work, mainly they work numerically. They show that this complex classical system can exhibit tunneling effect, tunneling-like behavior as in quantum mechanics. In fact, this paper is the only one that I know about the mathematically rigorous studies about from this point of view. Back to embodied problem, another motivation comes from the work of Alain and Vadim Kalyasin about the finiteness of central configuration. Exactly, they use the ideas of complexification of the equation of central configurations. Then they use the tools from complex algebraic geometry to get the very precise estimate about this finiteness. So these are the motivation for me to study the dynamically of the complexified planar Kepler problem. So now, how to complexify the problem? As you have already noticed that we need to treat the square root of this guy. So when we complexify the problem, you have this is multi-valued. The square root of it is multi-valued. So we follow the idea of the Riemann surface of the square root of that with that complex variable. Roughly speaking, we just double this x1, x2 configuration space to accommodate the multi-valueness of this function. More precisely, we need to do like this square root Riemann surface in a family version. So I take 2 copies of C2 with this set delete. So notice that here I need to delete a cone instead of a point as in the real case. So I take 2 copies. One is denoted by Qi, the other is denoted by Q2. Then I introduce 2 new coordinates. Just combine this x1 and x2 in a special way. In this way, the sum of the square can be written as the product of this psi1 and psi2. I cut along the negative real numbers of this product. Then for each fixed psi2, I do the same thing as for the Riemann surface of the square root. Then I glue them together for varying psi2. In this way, I get a new configuration space. This is the picture to show how do I glue the 2 parts. This is the same as in the square root Riemann surface. Then we can prove that the configuration space is a complex manifold dimension 2. The phase space is just a cotangent bundle of this manifold. One can check that this is a trivial bundle. Also, I can get this symplectic form. Now here, this symplectic form is holomorphic to 0 form. This is quite different to the Euro Keller form. Keller form is just a holomorphic, it's a 1-1 form, but here is a 2-0 form. Normally, this is called holomorphic symplectic manifold. This is our phase space. The Hamiltonian now is well-defined and it's holomorphic. So for this complexified planar Kepler problem, we have this holomorphic Hamiltonian system. Now we consider the symmetry of the problem. As in the real case, we have the symmetry group, but now it is SO2C instead of SO2R. So this corresponding to the rotation, but in the complex meaning. So it's easy to check. Still, this group preserves the Hamiltonian and it acts on M in this way. But here K means it's either I1 or 2. It depends on which part we leave in Q. So here is the symplectic action. So one can check that, in fact, this action is still Hamiltonian action in our new symplectic form with moment map, the same form as in real case, but now it's here x1, x2, y1, and 2 are complex. So now I have this complexified phase space with 2 holomorphic functions, which are first integrals of the system. So we can prove that this is still a Liouville completely into system, but it's in a holomorphic sense. In fact, there is another way to write this action neatly. This means that I need to introduce 2 more variables. The form looks like this part. Notice that this psi1 and psi2 are not equal to 0 because of their product is just this one. This one we have deleted in the configuration space when this guy equal to 0, we have already deleted. So this one is always non-zero. So using this coordinate, this phi can be written in this way. So you can see that this is just a kind of scaling. Here lambda is a combination of this A and B, with B multiplied by I. And notice that here A and B are complex. We can prove the following propositions about this action. First, this action, this C star action is free and proper, and this map with the image C1, C2, C3 defined in this way. In fact, C1 is just this C4 is the Hamiltonian. This C3 is just the angular momentum writing in these new coordinates. You can see that C2 is part of this C3. So this C1 is the denominator of this Hamiltonian. So this map is just the quotient map of this C star action. In fact, we can characterize the map, the image of the map, by this algebraic site in C4. You can see that this is the polynomial to define this the image. Of course, we need to delete the point where C1 equal to 0. In fact, this map gives you the bundle structure of the action. So here is a picture to show the situation. So this C2 is the coordinate, C2 is the C3, C4 part. So this vertical direction is C1, C2. So this R is the image of the with the fiber the C star action. So for each point sitting in this R, the pre-image under this pi is C star. So now I fix a value C, I denote by C this C3 and C4. Now when C3 and C4 are fixed, this polynomial equation becomes an algebraic curve. So this curve, it can be checked easily that this curve is smooth when, if and only if this C does not live in this discriminant. Also, it can be easily to determine what the curve looks like. For example, when C4 equal to 0, this curve is just the complex plane. When C4 does not equal to 0 and this discriminant is not equal to 0, this one is a generic situation. This curve is homomorphic to C star. Note that this C star is not the fiber of the projection pi. It's another C star. When C4 is not equal to 0, but you are sitting in the discriminant, the curve is degenerate to a conical surface. So pictorially, the situation looks like this. Here is the generic fiber. It's the generic situation. The curve is just a C star. When you are sitting in this axis is C4 equal to 0. The curve is C. Here is the point sitting in the discriminant. The preimage is a conic cone. So for us, remember that I also need to delete the point where C1 equal to 0. So I denote this algebraic curve with the point such that C1 equal to 0 this means that there are 2 points for each curve. There are 2 points that I need to delete. One is 0, 0. The other one is 0, minus 2, IC3. I denote this curve by RC. Also, I use MC to denote the level set of the energy momentum map. Here is the picture for RC. So you already know that this curve, but now I have 2 points deleted. This corresponds to the points where C1 equal to 0. This C star is the fiber of the C star action. So here, this guys I denote by RC, the algebraic curve. The level set of the energy and momentum map I denoted by MC. You see, this MC includes 2 parts. One is the fiber of the action. The other is the algebraic curve. So, inspired by this kind of works from quantum molecule spectroscopy, we try to study the monodromy around the discriminant of some period lattice. Now I tend to people study this because the general idea is that the monodromy of the singularities in such kind of completely integrable Hamiltonian system have some quantum effect. Now I tend to the period lattice. I take some open subsets in this phase space. I delete the point, this C2 plus IC3 equal to 0. In this set V, I can use another set of variables as our new coordinates. In this new coordinate, the symplectic form can be written in this way. So here is wedge DC3, here is wedge DC4. So I just draw out this part, and this part, I get 2 new holomorphic 1 form. You see, this is a holomorphic 1 form. This is another holomorphic 1 form in V. These 2 holomorphic 1 form play very important role later on. So I denote one holomorphic form by omega 1, the other one by omega 2. I use these 2 guys to define some generalized Abel-Jacobi map. This means that for each point, I follow a path from P0, I fix some P0 to this point P. As well known, this omega 1 and omega 2, which I can prove that they are closed. So this Abel-Jacobi map depends only on the homology class of the path. Also, it's well known that this Abel-Jacobi map is multi-valued. This multi-valuedness can be determined by the homology, the first homology class of this level set. So I need to determine this homology group. This is a picture to show the multi-valuedness. So I skip. So for each gamma in this first homology group, I use these 2 closed holomorphic 1 form to define vector in C2. This one will be of period lattice. In fact, as shown by the previous pictures, you can check easily that the first homology class of MC is Z to the power 4, and the first homology group of RC is Z to the power 3. Here is when C3 is not equal to 0. This is our first result. here I use gamma 1, gamma 2, gamma 3 to denote the basis of this homology class. Pictorially, it looks like this. This gamma 1 is around this. Here, this RC is a generic fiber. Remember that for generic fiber, you always have the C star. So this means this the origin of the C is deleted. So I have a nontrivial homology class around this this one. These 2 points are deleted due to the I need the C1 is non-zero. So this means that these 2 points correspond to C1 equal to 0. So I have 2 loops, non-trivial loops around these 2 guys. So I denote this by gamma 1, gamma 2, and gamma 3. They generate the first homology group of RC. I can define mu and nu. This is part of the holomorphic one form omega 1. This is the omega 2. I use this. I can claim that this RC defined here, in fact, it's a lattice in C2. So this is called the period lattice. In fact, this lattice has their rank 2, and it's generated by 2 vectors. One is the vector with component mu and nu. The other one is a constant vector, it's 2 pi 0. So maybe I give a very brief introduction to the ideal proof. So for this point, this point corresponds to one of the 2 points that I need to delete due to the requirement that C1 is not to 0. So in fact, this one is the removable singularity for this differential. So this means that this integral is 0. So for this point, this is non-point that I need to delete. So this is in fact the first order pole for this differential. So this one gives you the residue, but the residue depends on whether C3 is 0 or not. If C3 is not 0, this one is in fact it's minus 4 pi. If C3 is 0, the residue is minus 2 pi. The contribution is different. In fact, with this new coordinate, this MC, the level set of the energy and energy momentum map, and this attribute curve times this group action group. This is a diffeomorphism. I use the image of this RC. I take this gamma to be any closed path in MC in this level set. In fact, we can deform it to make this gamma lie in this part, in this set. So the image of this gamma in RC, this means that I use the projection pi from this MC to RC. Just forget about this part. This part is from the group action. Any curve can be written, in first homology group can be written in this combination using the basis gamma 1, gamma 2, gamma 3 as I introduced before. Now I can the periods, for example, for omega 2 along the gamma. In fact, only contribution comes from this first part. These 2 parts because it's 0 due to this gamma 2 and gamma 3 are the loop encircling around the point that I delete. I have the requirement that C1 is 0. So these two parts, the contribution is 0. So for omega 1, remember there are two parts. One is from this Xi 1. Xi 1 is from the fiber part of the projection. And this is the in RC part. So for this part, as I said before, this pi gamma can be written in terms n1 times gamma 1, n2 times gamma 2, and n3 times gamma 3 by using the linearity. This period can be written in 4 terms. In fact, only this term gives you this part, because before I defined this as mu. As I explained before, this one is 0. This one is 2 pi. The contribution is 2 pi or minus 2 pi or minus 4 pi. This one, in fact, gives you 2n pi. So I combine the contribution from this part, and this part together to give this 2m pi. So I combine the computations above, then I can get the result. So this is about the period lattice. Once I have the period lattice, so this is for generic fiber. For any generic C means C3 and C4. For each generic C3 and C4 in C2, this means that for any fixed energy and angular momentum, for generic one, I have a period lattice. Remember that. Look at this picture here. So just now I show you the result that's above this kind of generic point. I have a period lattice. Now I want to study the monodromy around this singular locus. The singularity comes from 2 parts. One is from the discriminant. The other comes from this C3 axis. Our next 2 results show that, in fact, if I choose the loop properly around this axis or around the discriminant, when I trace the loop once, this period lattice can have monodromy. Let me show you the result. So this is the first result about the monodromy. This is the monodromy around the discriminant. Remember that above the point in this discriminant, the fiber is a conical surface. In fact, we can prove that there is a non-contractible loop gamma in this C2 with this discriminant deleted. You have this bundle of period lattices. When you travel around this gamma once, you have nontrivial monodromy group, monodromy matrix in this form. More precisely, we prove this theorem. So we have 2 differential forms, omega 1, omega 2 on RC, as I defined before. I can choose a path, a closed loop, gamma in this space. When I travel around this gamma once, one can show that the period of this alpha turns into minus 4 pi minus this guy. And the period of omega 2 just change the sign. So this gives you the monodromy matrix of this one. The rough idea to prove this theorem is that first we normalize the curve RC. Remember that for each C, we have a curve. But if you try to calculate the lattice for each C along the curve gamma, so it's hard to control. So the first idea is to normalize this curve into a uniform. Then we find that the period of alpha and omega 2, I can choose a closed path in this one. Then it's quite easy to study the monodromy in this situation. So more precisely, if this C3 and C4 does not belong to this one, I'm sorry, it should be, this is belong to this one, and C4 is not 0. The curve, I can write the curve RC in this new form. Then I do this substitution. This one this transformation gives you the canonical form. I mean the uniform way to write down the algebraic curve. Under this transformation, the one forms alpha and omega 2 change. So they look in this form. Also, the pole of alpha, this pole 0, 0, will be transformed to the point on this curve. So before, on above each C, I have a curve. Now, for all of the C along the gamma, I have one curve. But I have many poles. In fact, one corresponds to each C in the gamma. Now I choose the path that I follow to study the monodromy. This is a special point in this discriminant set. I choose this circle gamma with center at this point and the radius less than 1/2 in this complex plane. So this means that I choose this closed loop in this plane with C3 coordinate fixed to be 1. With this closed path gamma, the period of alpha and omega looks like this. So this is a picture to show that now this whole picture is the curve, the only curve that I have for transforming. The poles along the gamma that I choose above, we have a family of poles. This poles. I need to avoid this poles to calculate the period. So this is the path on the curve, the common path that I use to calculate the period. Not this curve, not this circle. This circle sitting in the C3, C4 plane, but this curve is this circle is the curve to be used to calculate the period on the given curve. So here you can see that along the chosen curve gamma, I have this period in this form. This minus 2 pi, just due to the special, just due to my choice. When this C4 goes through this gamma once, this integral does not change. But notice that there is a prefactor in front of this, but this one changed sign. So this means that this period turns into this form. So this gives us the first part of our result. Similarly, you can calculate this second period. This one just changed the sign when you go through this gamma once. So this gives you this result. Another nontrivial monodromy comes from the nontrivial loop around this C3 axis. In fact, the final result turns out to be the same as before. We still have nontrivial monodromy matrix. In fact, the monodromy matrix is the same. This is a precise statement that I choose to skip. That's all what I know up to now. Of course, for us, it would be great if we could determine the whole monodromy group. But the first problem to solve is to calculate the group, this algebraic set, the complement of this algebraic set. Remember, these two parts, this one corresponds to the discriminant, this part corresponds to C3 axis. These two parts is the points that I need to delete. This part corresponds to the singular fibers. So the complement corresponds to the regular fibers that for each regular fiber we have this rank 2 lattice. If we want to determine the whole monodromy group, the first step is to determine the fundamental group of this guy. In fact, now I could not prove that. I cannot calculate it, but I guess that the fundamental group could be d to the power 2. This means that the two nontrivial loops are in fact the generators of this fundamental group. If this is the case, the monodromy group would be Z2, direct sum Z2. But now I could not prove this. This is one of the problems that are left to be solved in the future. Of course, still there are a lot of problems related to what we have done. I think that the most interesting one would be the dynamical meaning of this nontrivial monodromy, as suggested by these works in quantum molecular spectroscopy. Up to now, I don't know how to answer these kind of questions. Also, there is another question. Maybe you may notice that this monodromy matrix, you see the diagonal part is -1 and 1. This is a unipotent matrix. One of Russian colleagues asked me this question. So is there any physical meaning for this unipotent property of this monodromy matrix? No, I don't know how to answer him. That's all for the planar Kepler problem. Of course, I think the more interesting one would be the complexified three-dimensional Kepler problem. For this one, as you already know that there is this famous eccentricity vector. This can gives you more symmetry of the Kepler problem. I guess that if I could solve this at least the monodromy problem for this complexified three-dimensional Kepler problem. Maybe I can say something about this. Of course, up to now, I don't know. The other question, maybe it's more geometrical, is so you notice that now after the complexification, the configuration, the free space becomes a holomorphic symplectic manifold. In fact, this one, I mean, at least not exactly the same, but they are quite closely related. The other one is hyperkähler manifold. This kind of manifold play a very important role in mathematical physics and in geometry and physics recently. So you see, even we don't consider the dynamical problems, still the free space is already very interesting. So I would say that this is a fascinating problem to study the interaction between this interesting geometry and the dynamics around on this manifolds. This is the problem that I try to pursue in the future. Okay, maybe that's all. So maybe I stop here, and thank you, and happy birthday to Professor Hildeberto Cabral. Thank you. Thank you.
Thank you, Professor Shanzhong, for the excellent talk. And anyone have questions or comments?
Maybe I have one stupid question. Is there any relation? I remember, I just remember the title of a talk by Holger Dölin about monodromy in the Kepler problem.
Yes.
So is there any relation? I don't think it was complexified in this case. Maybe Alain.
You mean he considered the monodromy of classical Kepler problem, right?
Yes, yes. But he said there is a relation with the eigenfunction in the quantum case, but I don't remember the talk. You just look at the title is monodromy in the Kepler problem.
Oh, I'm sorry, I don't know that there were.
Yeah, Holger Dölin and Holger Walkens.
Yes, I met in Paris. I met Dölin.
Yes, yes.
Yes, but I don't know his work.
Okay.
I should check. Yeah.
And my second stupid question is: suppose you regularize by Levi-Civita the problem, then you get an oscillator. So is there any relation with the complexification of the oscillator?
Yes, in fact, I try to understand this problem. In fact, just before I gave this slide to the organizer, I delete one slide, one page. It's about this problem. Still, I don't know. Yeah, I guess that this week maybe gives you a better way to understand this regularization problem. I guess. I don't know now. Thank you for a nice question.
好的，谢谢。
谢谢你。
Thank you.
Hello.
Yes.
Maybe I have a question.
Yes.
Yes. Yeah. Sorry, I missed the beginning of the talk for technical problem. Please send me the slides, Shanzhong.
Yeah. Yes. It's my pleasure. Yeah. I can send you also the paper.
I have just a comment about the slide that just disappeared. It's about the dimension. You said dimension 3, you have SO4 symmetry. But indeed, this works for any dimension. I mean, if you have Kepler in dimension 2, then you have SO3 symmetry and so on and so on. And so on.
Yeah. You mean the one dimension further. So the work of Moser, right?
Not exactly, but...
Not exactly. Yes, I know your lecture. In fact, the receive lecture. Yes. Yes. Thank you.
Yes. But in the receive lecture, it's not the true symmetry. Maybe you can say you can look at the paper by. Papers too complicated. Sorry.
Yes, maybe you can send me the reference about that.
Yes, yes, yes.
Okay, thank you.
Thank
There
you,
is that
Alan.
one by Sternberg, right?
No.
Sure.
Cushman, and Wistermat. Cushman, Wistermat is doing the thing in any dimension, even 4, 5. Cushman, Wistermat.
Okay. I will check it.
Okay. Anyone have questions or comments?
Okay. Is any hope for the three-body problem?
I don't know. So, I mean, if this one is, you see, this problem is a little bit. You need to the knowledge from complex variables. Normally, people working in celestial mechanics are not familiar with this kind of complex algebraic geometry. So, in fact, when I studied this problem, I need to start to learn some algebraic geometry. So, for general three-body problem, I think it's really hard.
Yeah. Well,
of course, maybe there is some benefit. Yeah.
So even for two-body problem, that I was expecting your monodromy group to have something like a Z3, that is the cyclic group of order 3, and somehow that your result does not have that. The reason that I think that why you should have a cyclic group of order 3 is that in a real analytic case, that if you look at a two-body problem, the singularity corresponds to a solution where you have a branch point. That is, if you look at the Kepler's problem, expansion at singularities t raised to 2/3. So if you look at the solutions of a two-body problem, at the singularity, if we complexify the time t, you have a branch point. The branch point has a 3 branches. It's 1/3. So I thought when you complexify this problem, and you should see something to reflect that, because if you do any continuation, you complexify the solutions. You have to go through branches, 3 branches, and that returns back. So that I would expect should be the part of your monodromy group. But somehow I do not see that. I don't understand why. That's not in the.
For me, the problem, the time is real. I only complexify the configuration variable and the phase space variable, not t.
Yeah,
maybe
I understand.
If I complexify t at the same time, maybe I can see this Z3 symmetry. Probably.
Yeah.
I haven't tried.
Right. Yeah. No. If you complexify time, then you definitely should see the branching of
I think so,
of the singularity. So, but that somehow has to be reflected in your vector field. Still, even if you don't use your complex time, but your complex vector field, that should be reflected, because it's a simple continuation of the complex solutions. And
I see.
Well, then that should be part of it. I don't see why that your result does not show that.
I just follow the idea of, from these physicists. They insist that the time variable should be real. In fact, I don't
doesn't matter. I mean, it's basically analytic continuation. So if your time variable is real, but you continue your solutions that are around whatever the time, complexified time, you should get still you stay in your complex vector field.
You mean I deform T to complex, right?
You don't have to use specific T, but because you're looking at the complex vector field anyway.
Okay.
But I don't know. Just some.
Thinking in the suggestion of Professor Shia, and taking account your talk, maybe your approach, it's possible to adapt your approach for choreographies in the three-body problem. I cannot hear question, but
clearly.
Huh?
Sorry, I cannot hear you clearly. I'm sorry.
Sorry. And I'm asking if your approach, it's possible to use your approach to study choreographies of the three-body problem in the complex domain. Maybe I'm making a dumb question, but if you have if the bodies are making a choreography that satisfies some algebraic curve and with no trivial symmetry, maybe it's possible to apply tools of complex algebraic geometry to extract information. If they do you understand my question?
In fact, I could not hear very clearly.
Sorry.
I can get something here, but I haven't thought about that. Maybe you can try that. I don't know.
But usually choreographies are not along algebraic curves.
Yes. But maybe it's true. It's true.
So another question that since you have non-trivial monodromy group,
yes.
So does that imply the complex two-body problem is not integrable?
No, this natural monodromy comes from the singularity of this holomorphic integral system.
Right.
I mean, it's still integral, but it is a singular integral system.
No, that means your integrable. Your integral has it's not. It has to be on the covering space. It's integrable, but not in the phase space itself. If you have a non-trivial monodromy group.
You mean now the phase space is modified by me? You mean in the non-modified phase space, right?
No, integrability means you have a function, right? You have a first integral, but if you have a non-trivial.
Hello?
Yeah.
Sorry, I cannot get your last words.
All right. Is it okay now?
Okay.
Yes,
now it's okay. Yeah.
When you have non-trivial, typically in classical integrability theory, you can prove something is not integrable by proving non-trivial monodromy group. That's a large theory. A lot of papers on that.
Yeah, difference Gauss theory.
Non-trivial monodromy group implies non-integrability.
But that natural monodromy is along some
periodic points.
specific, yes, periodic
If you have
solutions.
periodic solutions, you have no
If you
trivial.
consider the variation equation, then you get this natural monodromy, right?
Then it implies non-integrability. But I'm not sure in your situation whether that's the same case.
I would say there are different situations.
Right.
What is the definition of complex integrability?
Enough first integral?
Yes, I just follow the Liouville integrability, but in the holomorphic sense. For me, it's the definition of integrability.
I don't know how basically how you treat time, right?
The time is real as euro. But,
yeah, if your time is real, then that you have 4-dimensional space instead of 2-dimensional space.
Yes.
Yeah. So I don't know. I have no idea. Only the classical integrability, the relations between integrability and a monodromy group. No, I just a question.
Okay. In fact, I don't know the relation between this one, my work, and what you have mentioned.
Yeah, there's a classical theory on monodromy and integrability.
Yes.
Maybe I can just comment on Jeff's remark. Even we have more precise probably relation between. So this is called Ziegling theory, right. And for example, like Alexei Tsigintsev, he studied the free body problem with relation to Ziegling theory. So he computed the monodromy for let's say Lagrange homographic solution of the free body problem. And of course, if you compute this monodromy, this implies that he computed also the monodromy for the Kepler problem in some way. And maybe not exactly yours, but in some way, very so. This will. Yes.
Okay, I need to check this, whether it's the same or not. Yeah.
As Alan said, it's a Ziegling theory.
Ziegling theory, yes. It's
Ziegling
a classical theory, yeah.
Very classical stuff.
Okay. Anyone have comments or questions? If no, then we would like to thanks again the Professor Shanzhong and
thank you very much.
Thank you. Amati, what's next?
We can